Okay, this is the final video that I will upload. I'm just going through the main functions of Gretl. Once again, I did this in the lecture, and on the lecture slides you find most of the relevant functions for you. I think using the program in itself is quite simple. What I would really suggest you to do is to think about your data and think about maybe what you want to say and how you can use this tool a little bit more creatively than just plugging in the numbers and clicking a button. But that's mostly what Gretl is about, of course. So if you want to start to work with Gretl, you can actually pull Excel files, even files from other statistics programs such as Stata or something into this window here, if you would want to go this way. Another thing, and what I'm now going to do, is to use a sample file, which you can find here under sample files, and there are a lot of examples of different data. In the lecture, I used data by MenQ. So down here, you find the MenQ, Roma, and Val cross-country data. This was really just an example, right? So you can use any other type of data. Of course, you are going to use your data. I can just double-click this, and Gretl opens this. And this is pretty much the same when you open a file. It will open one more window that tells you you have opened a file, and you can just click it away. It's fine. As long as you see your variables under variable name, you are good to go. Okay, function-wise, the first step is really just about loading data, and you can change your working directory if that is necessary, but usually you don't need this. Under tools, you find a few helpful tools, but also not really interesting for you. The only interesting thing for you might be the non-parametric tests, although we haven't really talked about these, specifically the correlations. You can calculate a Spearman's correlation instead of a Pearson correlation of two variables. If you wanted to do that, you can do this. But as I said, we haven't discussed this really, and this is just for people who are interested. Yes, Gretl can, of course, do that as well. Under data, you find a few interesting things on displaying values of a variable. So if you have a variable selected, you click display values and you can look at the values within that variable. You can hold shift and select multiple variables and do the same, and you get a list of all of the variables. Added values is obviously if you want to edit one single value in your dataset, but usually you do that, I would suggest, in Excel or outside of Gretl. Same for add observations, right? You can get some information on your dataset. There is the possibility to give variable labels, and here we also have descriptive labels, but you see that dummy equals 1 for non-oil producers. This is something that you can tell the program so that you know when it gives you a 1 that this is a non-oil producer and not an oil producer, okay? So basically, it's just kind of a node that is attached to a dummy variable. Whenever it is taking the value of 1, it's a non-oil producer. Or let's say you have a yes-no variable, but you don't remember whether yes was 1 or 0. I mean, most of the time it is 1, but you can't be sure maybe, so you can add a value label if that is necessary. All other functions are not that interesting. You can count your missing values, which is maybe a little bit interesting if you want to know how many missing variables you have very quickly. You can take away this here, so you don't show it for each observation. This gives you an overview of all of the variables in your data set or that you have selected, and then their respective missing values. And you can also count missing values for each observation, and you get a list that tells you for here each of the countries that are selected what is going on there. Okay, so you can, under view, calculate summary statistics, correlation metrics, so very simple stuff. You also find this principal components analysis, where you remember it means you try to reduce many variables to maybe one. So let's say you have a lot of variables where you think they represent an underlying thing. These are potentially correlated, and they are not only correlated in terms of the numbers, but you have a theoretical explanation why they would be somehow, or why it is necessary to merge them, right? So that's what you do here. And you have the Mahalanobis distance, but we haven't really discussed this. Under add, you can add quickly, logarithms of a selected variable. You could try this if you have problems with your residuals not being normally distributed, if there's problems with outliers. You can try and see what happens with a log. Remember that this changes really the interpretation of your data. If you log everything, you basically get like percentage changes or elasticities. With the squares of the selected variables, you get square terms, and you can have nonlinear effects. Once again, remember this as well. If you square a variable, you get more or less a U-shaped effect, either an inverted U or a simple U effect. With the index variable, you can add a variable that just goes from 1 to whatever the number of your observations is. This is useful if you do not have such a variable yet. You should always have one variable that simply numbers your cases so that you can identify them at all times. You have a lot of gray here, which is because these things are related to time data. Okay, this is it for the ad. Under the sample, you can restrict the sample. For example, let's say you just want to have a certain subsample of the data that you have. You can use a dummy variable if you have one. For example, you have OECD and you click OK, then this filters everything just based on OECD. So you subsample based on this variable. Only if this is 1, so if it's an OECD country, it will stay in the sample. You can also enter a Boolean condition, and if you click help, here it explains to you how this is done. So Boolean conditions are, of course, these and or things, and basically you can tell the program what data to use and what data to avoid, or certain data ranges or certain observations. Read through this if you think it is necessary for you, but since your data sets are probably not that large, you can also do this in Excel and just do several Excel files with different samples if you want to have subsampling, which could be interesting depending on your data. So that's it for this. And then we come to the variable window. Here you have a few graphics that you can plot per variable. Again, the summary statistics and so on. But I will not go into this. And then finally, you have the model page. On the model page, we have just discussed the ordinary least squares. All of these others are most of the time variants of the ordinary least squares. So, for example, here on limited dependent variables, for example, it could be that your variable just takes a value in a specific range, or it is just a 1 or a 0, like a dummy variable. In these cases, you have to use different types of models. They operationally function the same as OLS, at least in terms of using them, technically speaking. But their interpretation sometimes is a little bit different, at least with these 1 and 0 variables. But we are not discussing that here, of course. Then you also have robust estimations, which are some estimations more robust to problems in your data, such as outliers. As I told you, in the ordinary least squares function, you have, if you click this, you have this robust standard errors option here, which I would always at least try to see what happens to your results. Refer back to the lecture slides to see what this actually does, and also maybe read a little bit about it. It's quite necessary sometimes to use this. If you have heteroscedasticity problems, for instance, or autocorrelation problems, these robust standard errors can help to mitigate this. But then again, it's always necessary to look at your output of using them. Has this really improved your interpretation, or does it change your interpretation really? That's, I think, the most important thing that you should keep in mind. Does it change my interpretation of my results or not? So if we wanted to do a simple OLS model in this case, what we can do is take GDP in 85, for example, and take, I don't know, the investment rate and being an OECD country, which is a dummy variable. And we just, for now, click robust standard errors, and we click OK. And this gives us the output window. I've explained all of these in the lecture, and you should read up on them a little bit to know intuitively what some of them, or the most important of them, mean, and the most important ones are indicated on the lecture slides. Of course, adjusted R-squared is our favorite measure of the variation explained by the model that we've calculated, so 50% in this case, and the archaic criterion we can use in order to compare models. So this is the result that we get. Remember that this means that it's a very small number. Don't be confused. We still have 3 stars, so this is so small that we have a highly significant result. So being an OECD country, you see, as a strongly positive effect coefficient. And for the interpretation of the coefficient, again, see the slides and supplementary materials. It is important that in the model window, you get other options up here. And these are the options where you can test for things. So you can use the Ramsey reset test to test for, let's say, square terms. You think maybe your square terms are important, and you take a look here whether squared terms would change your model or not. And for the interpretation, again, look at the slides. You can test formally for heteroscedasticity. I haven't done this in the slides because I've suggested to take a look maybe at the residual plot, and specifically to try to use heteroscedasticity robust standard errors, and maybe see if that changes things first. And this is it's not the, let's say, the proper way to do it, but it is one way that gets you at least a good result, or you can be sure that your results are not too biased by heteroscedasticity by doing that. But you can also test for these very simply with the White's test, for example. And if that would turn significant, we would have heteroscedasticity, which we now don't have because we're using the standard errors. Now, we can test for the normality of the residuals, as you remember. And again, this must not necessarily be a problem because it does not always change your results. But if you fear that it is very much skewed, then you can, of course, try to correct this with the appropriate tools. And then you have the option save, where you can save some of these statistics and make some additional calculations. Under graphs, you can plot the residuals by themselves or against another variable. And you can also look at the fitted actual plot by observation number. And finally, there's a residual QQ plot, which also shows you whether this is a normal distribution, which in this case, it is not really, but we're not going to fix this right now. Under analysis, you have some other options in terms of collinearity. I think this is the most important one that you want to check. Is there collinearity in my model? And you get the VIF, variance inflation factors. And once again, please look at the lecture slides and look in the literature to see what they actually mean. But it is quite intuitive in terms of what they do. And that, I think, is pretty much it. Oh, and there was the influential observations. This is something that I find particularly interesting because it can give you an idea, specifically when you have a smaller data set, which of the observations here are maybe somewhat problematic. Okay, so, and we have talked about the leverage, indicating a leverage observation here. And this could, of course, be potentially a problem. And you can also look at the DF fits. For some more in-depth explanation of this, I have added a document to the .ip folder, and it's a very hefty document. It's very large, but it also includes all the functions of Gretl. And if you're interested in leverage and influence, it includes one part on that as well, but it's not necessary to know this. And this is basically it. So basically, the point is for you to run a regression, a simple OLS model, and to see where this gets you. If you get problems, if you even get significant results, maybe you can experiment a little bit and try to improve your model. and think about maybe why it doesn't work. So do not be too concerned if this is not really what you get, but you get a mess, more or less. This can happen because it's real data that you're using. But try to communicate to us what the problems might be and what types of data you could use to improve. And maybe you can interpret some of the signs of the coefficients. If the coefficients are not near zero, it is sometimes legitimate to at least very carefully say something about their direction, okay, even if they're not significant. Although you have to be very careful with this, but I will allow you to do this. Okay, so with this, I think I covered most of the Gretl things, and good luck for your presentation.